Okay, so we're looking at this now second worksheet, and remember these worksheets, they're voluntary. You don't have to do them, but I think that they're going to be really helpful for you in terms of digesting the material and really highlighting some of the things that I know students have struggled with this in this class for some time as I've taught it. And so in our second worksheet, we're going back to really chapter 3, and in chapter 3, the major topic is acid-base chemistry. It's a topic that you've had before. It's certainly a review. But I wanted to go ahead and highlight two things using this worksheet that I think are going to be helpful for us moving forward, and also things that I know students struggle with. Okay, and the first thing is this: in terms of moving forward, I have described acid-base chemistry in terms of the affinity of a conjugate base for its proton. And that word affinity is really important because when we are moving into other topics in this class, in particular when we get to later chapters like chapter 7, chapter 8, and chapter 9, we'll be thinking about the affinity of proteins for certain things in their surrounding environments. For instance, the affinity of a protein for its ligand, or the affinity of an enzyme for its substrate, and we'll be using dissociation constants or equilibrium constants to define the extent that a protein has, or the extent of the affinity of a protein has for its particular substrate or ligand. Okay, and so there'll be a quantitative measurement, and we'll be comparing one enzyme to another or one protein to another and their affinities for ligands. Well, we can do the same thing with acid-base chemistry. It's not something that you normally talk about in general chemistry, but I think it lays some important groundwork for us moving forward. Okay, and so what we really have here is in this first activity, we have these two molecules, propionic acid and then glycine. And so let me go ahead and draw those things out for us, so we have some context for these things. That's meant to be a 3. Let me redraw that. There we go. And I draw a rough sketch of the structures of these two molecules. Okay, so this would be propionic acid. Its pK is about 4.87, thereabouts. Okay, and then glycine is going to look very similar. Okay, so if you've gotten into chapter 4, you've already looked at amino acids. Okay, and so glycine is one of the simplest amino acids, and it looks something like this. And its pK, what we would call pK1, is equal to 2.34. Okay, and when we think about these pKs, we're really thinking about this carboxylic acid and the fact that in a titration, that carboxylic acid can be protonated and deprotonated, okay, depending on our point in our titration curve and the pH within the surrounding solution. Okay, now as you look at these two molecules, right, they're very, very similar. Okay, in fact, I drew them identically, and so I have to give myself a red check minus because I just realized I made a mistake here. That's fundamental. So let me go ahead and get rid of this. Some of you were like screaming, "No, you made a mistake," but I corrected it. Okay, there we go. But I gave myself a red check minus. But anyway, okay, so that's glycine now. But in any case, they're very similar. But when you look at them and you look at their pKs, the pKs are quite a bit different. Okay, now you can pause it after I ask this question and really think about this. Which one of these molecules exhibits a greater affinity for the proton on the carboxylic acid? So pause it and think about which one and answer that question. Okay. Now, after you do so, hopefully you came back and said, well, the pK that's the largest or the highest represents the greatest affinity of a conjugate base for its proton. So we would say that then this molecule, propionic acid, has a greater affinity for the proton than glycine. Okay. Now, what does that really mean, though? And I think that it's important to think about this in terms of what's happening in, let's say, a beaker. So let's go ahead and draw this out. I'm going to use this. Oops. So we'll just draw a reaction vessel. We can say it's a beaker, okay? And what we're thinking about here, we'll go to more general terms. We're thinking about this type of chemistry, right? The equilibrium between the protonated form and the deprotonated form of our acid. The deprotonated form being called the conjugate base and the protonated form being called the acid, right? And so we've got that equilibrium there, and then we can just put this right in this beaker. And something we want to remember and really think about in terms of the pK is that the pK represents the pH in which the conjugate base or the deprotonated form is an equal concentration to the protonated form of the acid. So if we were to do this, okay, let's go ahead and pick green here. We're going to draw here the protonated form. We'll put HA, and then we'll put HA, and we'll put HA. Okay, so there's 3 of them there. Okay, we'll go real small numbers because it's easier to draw. All right, and then we'll put here the deprotonated form, and we'll put A minus, A minus, and A minus. Okay, so we have now an equal concentration of the protonated form and the deprotonated form, okay, of our particular acid, okay? And when we do this, and we represent a solution where they're in a 50-50 mixture, then we can say that the pH is equal to the pK, okay? So going back to our example here with propionic acid and glycine, it takes a pH of 4.87 to obtain this equal point, okay, where we have equal amounts of conjugate base and equal amounts of the protonated form, okay? Now compare that to glycine. Well, it takes a much lower pH to obtain that. It's 2.34, okay? Now, as pH drops, hopefully you recognize this, that as pH drops, proton concentration goes up. You get more and more protons, okay? So when we think about it this way, if I were to draw using, let's say here, red dots equal protons, okay, well, I can just start to put these in solution, right? And there's a certain number of them that represents a certain concentration. Let's just say that represents the propionic acid. That's the amount of protons it takes to get an equal amount of this and this, okay? Well, for glycine, we would have to, right, add significantly more of these. And remember, it's on a logarithmic scale, so we'd have to add a lot more, all right, to protons in the surrounding solution to force that A minus into the protonated form, or more of that A minus into that protonated form, okay? And so we just draw more and more of those. And that then is really what we're thinking about here when we think about pK as a representation of the affinity of a particular acid for its, or a conjugate base for its proton, okay? The more protons that are required in the surrounding environment to protonate that represents the fact that that conjugate base doesn't have a very strong affinity for a proton, because you have to have more and more of those. You have to really have to pack it, okay, pack the protons in to get them to attach to the A minus or the conjugate base, whereas as the pK goes up, it takes less and less protons for that conjugate base to remain or to obtain its protonated state. Okay, so that's really what we mean by affinity in this case, okay? And so hopefully this helps you think about what we are talking about with affinity, and it will actually help when we think about this with proteins and ligands. We'll just replace these HAs and A minus with PL, protein and a ligand, and the L, okay, with L representing ligand, okay? And then we'd have to have more and more of the ligand around to get it into the bound form, okay? We'll talk about that later, and we'll go into that in chapter, well, we'll start in chapter 7, really, in chapter 8, okay? Okay, now, the last question on our first activity of our worksheet is, why do you think that there's a difference in affinities, okay, between these two molecules? In particular, when you look at how similar they are, and this really goes a little bit beyond what we really need to really drill down into in this class, but I do want to represent this because I think it's important, because some of you might be saying, why is there such a difference in this, right? And it all has to do with this positive charge here in glycine that is just lacking or is not there in propionic acid. Okay, and that positive charge has an effect on this hydroxyl group on our carboxylic acid. One of the ways that we can explain it, we don't want to get too deep into the physical chemistry of all this, but one of the ways that we can just explain it is this way, and that is that we have a proton that is repelling, or I'm sorry, a positive charge that's repelling that proton, making it more likely to leave. Okay, protons have positive charge, there's a positive charge there. That's a decent explanation for it. Another way to think about it is that there is an electron withdrawing power, and this gets a little bit more into it, but there's an electron withdrawing power towards that nitrogen. Okay, and so that's going to weaken the bond between the oxygen and the hydrogen. Okay, all right, so, and then if you have a weaker bond, then you have not nearly as strong of affinity or interaction between that oxygen and hydrogen, and therefore the pK is lower. Okay, that's just lacking in the propionic acid. Okay, all right, now, if you haven't done the second activity, go ahead and pause it right now and go do that, and then come back and listen to this. That's really the benefit of this, is it gives you that practice. So you want to go practice these things, and then you want to come back and do this, okay? And looking at our second activity is this. It says, let's now move into amino acids. So this is really chapter 4 material. In fact, let's move into the amino acid lysine. Shown below is an amino acid in its predominant form at a pH of 7. The amino acid is triprotic with the following pKs. Okay, for this activity, you need to draw the predominant form of the amino acid at a pH of 11 and predict its formal charge. Okay, all right, so let's do this. All right, let me go ahead and give you a fairly decent strategy on how to solve these types of problems. Okay, so let's first of all just draw the amino acid in the form that we see it. It's the predominant form at a pH of 7. Okay, so we'll put it this way here. This is our alpha carbon. We'll put this here, NH3 plus, and then we'll use this here to represent our side chain. Okay, and that's lysine at a pH of 7. Okay, predominant form at a pH of 7. What we need to do is draw what the predominant form would look like at a pH of 11. Okay, and so how would we do that? And quite honestly, I think that the easiest way to do these types of problems is to go back and think about, well, what would the molecule look like at a pH of 0? Okay, and at a pH of 0, we need to understand that when you have that many protons in the surrounding solution, pretty much everything's going to be protonated. Okay, so if we were to put this at a pH of 0, so this is at a pH of 7. Let's go ahead and put it at a pH of 0. So C alpha, I'm drawing an alpha base as our alpha carbon. Okay, and then we would put a proton here on this alpha carboxyl group. Okay, CH2. This would be 4. I forgot to add that up here. That's 4. NH3 plus. And then finally NH3 plus. Okay, so we have everything in its fully protonated form. Let me go ahead and draw a line between these, and we're going to say this is at a pH of 0. Okay, and I think that that's probably the easiest thing to do, is that you just think about, okay, let's put everything in its protonated form, and then as we move up in pH, we can start to remove protons. Okay, now there's a couple of things to think about here when we do this. Okay, and the first thing I think you want to think about is, well, what kind of functional groups do we have on amino acids? Okay, so amino acids are very important in our upcoming discussion on protein structure and function. It's going to be very important for us to be able to recognize when a particular side chain in particular is going to be protonated and deprotonated, and what how it's going to be that way based off of pH. Okay, because that's going to define the chemistry of that particular functional group. Okay, and so what we want to do here is to just think about, well, in general, what kind of groups do we have within an amino acid? Okay, and what we have, first of all, would be carboxyl groups, okay, or carboxylic acids, and I'm just going to draw them as this, right? That's a carboxylic acid, okay, and in the protonated form, this is what those look like. Okay, and those can be found certainly in the alpha carboxyl group, but they can also be found in the side chains of things like aspartate and glutamate. Okay, now if we were to draw that in the deprotonated form, okay, you would lose the proton and it would obtain a negative charge. Okay. Now, the other type of group that's most commonly found in amino acids is an amino group. Okay, and in its protonated form, the amino group looks like this. It is a nitrogen with 4 bonds around it. It will have a positive charge. Okay, in the deprotonated form, the amino group would look something like this. Oops. Okay, you lose the proton and it would lose its positive charge. All amino acids have these at the alpha amino group, but many of the amino acids will also have these on their side chain. For instance, lysine has one of these on its side chain. Histidine would be another one. Arginine would be another one. Okay, now when we think about this, okay, so you have to kind of remember that. Okay, the next step in understanding this, well, how do I draw lysine at a pH of 11? Something that you need to just remember is this, okay, and that there is these fairly simple rules that we can derive from the mathematics found in the Henderson-Hasselbalch equation. But we can say essentially this, that number 1, okay, if pH is greater than pK, then the group, whatever functional group we're talking about, will be, I'm going to just put predominantly or predom, deprotonated. Depro. Okay, so this. So if the pH is greater than the pK, then the group will be predominantly deprotonated. And we can also say this, let me write up a second rule here. If pH is less than pK, then the group will be predominantly not deprotonated, but protonated. Okay? And this is all based off of the Henderson-Hasselbalch equation, but also just our understanding of pK. Even our last little exercise in this same worksheet, we talked about the pK representing the pH in which you have 50% of the protonated form of the functional group and 50% of the deprotonated form. Okay, so it's 50-50. Any pH below that pK, well, that's going to be predominantly protonated form. Okay, so, you know, greater than 50% will be protonated. Any pH above that, greater than 50% of the group will be deprotonated. Okay, so when we think about this, let's think about these things in terms of lysine. I'm running out of room here with my lysine molecule, but that's okay. I'll kind of crunch it in here. Okay, we want to think about this at a pH of 11. Okay, and one of the things that we want to make sure that we do here is look at our pKs. Okay, so we'll come back up here and I'll just draw the pK of this, what we would call pK1 according to our worksheet. Let me look at our worksheet because I can't remember the exact number here. The carboxyl group is going to be 2.18. That's the pK for that alpha carboxyl group. Okay, when we look at the alpha amino group, okay, the pK of that, pK2 is what we call this. Okay, in all amino acids, it will be the pK2. This is 8.95. Okay, and by that I mean that we label the pK for the alpha amino group as pK2. We always label the pK for the alpha carboxyl group as pK1, and the pK for the side chain, this guy here, will always be called the pKr. And for lysine, that happens to be 10.53. Okay, now what we want to do is we want to think about, okay, well, what is the predominant form of this amino acid going to be at a pH of 11? Okay, and we can just look back over here and think about this. And so let's do this. Let's draw our alpha carbon, and we're going to draw here, I'll use blue, the alpha carboxyl group. And the question is, okay, well, is it protonated or deprotonated at a pH of 11? Okay, well, our pK is 2.18, which means that the pH that we're looking at is definitely greater than the pK, which means it needs to be in the deprotonated form. Deprotonated form of the alpha carboxyl group is this. right up here. And so we're going to put a little negative charge there. Okay. Now let's do the alpha amino group. 8.95. Okay. Well, a pH of 11 is still in that greater range. Oops, not that one. Sorry. It's still in that greater range. pH is greater than pK, which means it's predominantly deprotonated, which means it's going to adopt this form, NH2. Okay. Now we can then finally do the side chain. Okay, and with the side chain, we are still at a pH greater than at a pH greater than the pK, which means it is deprotonated, which means that it would have to be this, and so we'll draw it as NH2. And now we have the predominant form of the amino acid lysine at a pH of 11. Okay, and so when you remember these things here, what our functional groups will look like in their protonated form and their deprotonated form, and you remember these fairly straightforward and simple rules, you can start to, of course, draw out amino acids in their predominant form at any pH based off of these things. Okay, of course, you'd have to know the structure of the amino acids, okay, to do so. Okay, so I hope this has been helpful. If you have any questions about these things, please, by all means, remember to contact me.